Hi, we are Team 11 and we are designing a dynamic balancer to be used by the future SUNY New Paltz students to conduct a dynamics lab. The members of our group are Maximus, a mechanical engineer, Mario, a mechanical engineer, Marcus, a mechanical engineer, and David, an electrical engineer. Our advisor is Professor Bird and co-advisor is Werner.
In this portion of the lab, static balance is achieved using the prototype disc designs. The student places a 10-gram mass at any position on the orange disc, setting an initial out-of-balance force that will need to be corrected. As seen in this portion of the video, using a wing nut, the student is able to lift the hinge motor in order to remove the belt at ease. This allows for static balancing to begin. The student is now observing the properties of the static imbalance and must figure out how to correct it using the correctional plane and mass. An equal mass is placed on the correctional plane at the same radius with a 180-degree shift, which will introduce a statically balanced but dynamically imbalanced scenario.
The student waits for the system to get up to a speed of 1,000 RPMs. The final design will have a tachometer mounted and will display the RPMs without the use of the handheld tachometer as seen in the video. Once the system is up to speed, the student will hit the start button on the user interface and it will calculate the acceleration. The results displayed will show the student that the system is unbalanced.
After the students have visualized the unbalanced system and calculated correct balancing masses, the latch on top is opened and the balancing weights are attached in their respective locations. The system is now dynamically and statically balanced, and the motor can be turned on to 1,000 RPM to visualize the balanced system. The user interface detects and confirms the balanced system.
These are the two potential user interface designs with different amounts of information that is output, allowing students to do math first, then check their theoretical results with actual results. The first is the one used for this video. It allows the user to select any time between 1 and 10 seconds and will plot the acceleration in meters per second squared for that duration. It calculates and outputs the average accelerations in both the x and y directions. It will also tell the user if the system is balanced or unbalanced based on parameters that we set. The second is a much more involved interface that requires the user to input the mass and location of weights for the new disc design, as well as the speed of the system in RPM. It will then perform the same acceleration plotting and calculations, but will also calculate the moments in the x and y directions and suggests a place and size of a counterweight to balance the system. This user interface can also be used for static balancing. Team 11 would like to extend a thank you to Professor Bird, Werner, and the State University of New York at New Paltz's Division of Engineering program for assisting us in our design project.